Today we will discuss one topic. We have one topic left. Then we will talk about final exam questions. Final exam questions, like which type of questions it will be, like that. So the topic that left for this course, it is called controllers. Controller is a very important element for the control system. So we will discuss different types of controllers in these lectures, like here the basic controller that is called on-off control. On-off control is like this. This is a switch, turn on, turn off. So this is called on-off control. Second one, we will talk about proportional control, proportional integral control, proportional derivative control, and combination of all these three, PID. So this one we call it P control. And this one, proportional integral, that is called PID. This proportional derivative, that is called PD. And lastly, we will combine all these three, and which is called PID control. These are the basic control of any control system we use. So, why we need this controller? What is the importance of this controller? Look, we already know this block diagram. We have explained it several times in this course. What we have in this? This is what? This is a feedback system, right? It is a feedback system or closed loop system. So this system, we call it feedback or closed loop. So what we have here, we have an input which is we call reference input, right? Which is we call it RT. Then in the output side we have CT. Now in feedback control, what do we do? We feed it back to the input again by using this point. What is the name of this point? Anyone? Summing point. So this is a summing point. And what do we get from here? We compare this and this, these two, and we get an error. What is the name of this error? What is this name? SSE. Steady state error. Now, what we learned before, that error goes through the plant and we get the output. What is plant? It is a system. We know that, right? System. This is a system. It can be first order system. It can be second order system. Anything, right? Like this K by Ts plus 1. What is this? First order. This is first order system. Or this one, omega n square s square cube zeta omega n is plus omega n square. What is that? Second order. system. Here, it can be any system. Then we get an output. How? By finding transfer function Ct, or in Laplace Cs by Rs. We know all this, we have done that in mathematical modeling, then time domain analysis, then frequency response analysis. But what if we don't know which type of system it is? We have a control system, but we don't know which type of system it is. Here we know it is given in the plan, first order system, second order system. Then we did the mathematical analysis. We do the mathematical analysis, but if we do not know which type of system it is, if this is unknown, if this is unknown, then how will you solve it? How can we analyze it? At that time we need a controller. Controller controls that system. So if your system is not known, if your system is unknown, then you need to use a controller to control your system. So here we use a controller. It can be any P controller, PI controller, PD controller, or PID controller, anything. So this controller, what it does, it will provide an output here. According to the controller, it will provide an output. And then that output goes through the plant or system. Then we will get an output, final output. So today, here, we will discuss this part only. This part. From this to this. And inside there will be a controller. So we will talk about this only. This controller. Today's lecture is based on this. So PID, mostly we call it proportional, integral, and derivatives. What is proportional, integral, and derivative? Proportional. Y equal to mx. Y equal to mx, which is y is proportional x. Proportional x. Proportional controller. So the output will change linearly. The output will change linearly. That is called proportional controller. Second, integral controller. What is this? Integration. Y is equal to integration of x dt. Rate of change. Rate of change. Integral controller. Derivative. Y is equal to dx dt. Derivative controller. Again, rate of change. Rate of change, rate of change. So this is linear. So these are the three. That means what? Here, what is x and y? X is the input, y is the output. This is input here. This is the input. This is the output. So here, in terms of this, we will call this is input in terms of controller, and this is the output. This is the output, which is actually here x is input and y is output. It is not the final output or input. It is only for the controller input and output. Controller get error, steady state error, and it will change the error according to the control. Proportional control, integral control, derivative control, and it will provide an output. We will talk about in details later on how it changed later. So this is the basics. So today's topic is this. There is an input that is error, steady state error, and that error will change according to the controller and we get an output. Now, why we need to do that? Because we need to make our error 0. This error, ET, which is SSE, equal to 0. We need to make it 0 to get a highly accurate system. Higher accuracy. If it is not 0, then your system is not fully accurate, highly accurate. To get a stable system, good control system has to be highly accurate. That makes steady state error 0. So here this error needs to be 0 and this controller makes it 0. So that's the basic of the controller. Next, that mostly the PID control we use because the general applicability or the usefulness of that in the control system. PID mostly the versatile controller that we use in any control system. I will tell you why PID is much more versatile or useful in terms of controlling than other controller later in the last of this slide. In particularly when the mathematical model is not known, I already told you what is the mathematical model. This plan, first order system, second order system, these are the mathematical model. If it is not known, then how can we control it? We need to use a controller. Mostly we can use it. Generally PID controller we can use it. So there are different types of PID control, basic PID control, modified PID control. So these are the common ones that we use to get a satisfactory control. That means making steady state error 0. To make steady state error 0, PID mostly are the versatile ones. In most of the cases, many industry, there are lots of industry. In all the industry, half of the controller are based on PID controller. Half means 50% controller are PID controller, because in the big industry there are large machines are operating. In those large machines needs to be controlled, and how it can be controlled? By using controller. So PID control is the common one because it is much more efficient than any other control. So now we will talk about each of the control, and we will talk about what are the advantages and limitations for each of these controls. So first one we will talk about on control, then P control, PI control, PD control, PID control. So first one is on off control. So look, what is this? This is a relation, input output relation in terms of control system. Here, the set point here, this is the set point, which is, we call it gain, right? Here, this one. So at the beginning the gain is decreased, then suddenly the gain increase, and it is fixed, it is constant. It is constant, the gain is constant always. We have seen that the gain is always constant. Now, this arrow, it is we call ET or steady state arrow. As the time increases, based on the gain, respective to the gain, the arrow also increases. So, this is the arrow. Arrow is decreasing, then increasing, decreasing, increasing, increasing, decreasing. Look, the gain increased here. Arrow increased. Look, before it was 150. Now arrow is 180. Why? Because the gain increase, arrow will increase. When the gain increase, arrow will increase. So the gain, arrow increase and decreasing, increase and decreasing. Okay. Now, what the on-off control does, it will make a binary output. This is the output. The controller output. How? Look here. The gain is decreasing. The gain is decreasing. Why the gain is decreasing? It is 0. It is on 0. And why in this point the gain is increasing? It will be high. It is high. Again here. While the gain is decreasing, it will be 0, low. So make it 0, 1, 0, 1. Here it is decreased till here. Now again it is increasing. It is decreasing till here. Now it is increasing again. So it will be high again. 1, 0, 1, 0, 1. What does it mean? This means off. This means on. This means off. This means on. So this is the controller output. It is a binary output. Binary. What is binary output? 1 or 0. This is the binary output. 1 or 0. 1 means high, 0 means low. 1 and 0, you know that. So 1, while it is on, 1 it will be on, while it is 0 it will be off, while it is 0 it will be off. By using this, we can control our device, we can control our system without knowing which type of system it is. By controlling on and off, on and off. Like LED, this type of LED. We can use this. This is analog control, we know, but we can make it digital control by using the controller. On and off, by using that. So this is actually the binary output. This is the output controller provides. That is MT. This is the output controller provides. So you see, it compares the gain set point with the error. This is steady state error. It is comparing these two, and while the error is decreasing off, while the error is increasing, it is making off. While the error decreasing, it is off, and increasing, it is on. Make it a binary output. So makes it an on-off control. So this is the simplest form. It is a common basic control, on-off control. Now let's talk about another one. We call it proportional control. P. So proportional control, mostly it is having a linear relation. I told you linear relation. That means what? Linearly it will increase or decrease. So linear relation, proportional. That means MT is proportional ET. MT, what is that? Output. ET, what is that? That is controller input. So MT is proportional ET. So we can write it MT is equal to Kp into ET. Kp into ET. So what is Kp? Kp is the constant value. Proportional constant value, Kp, it is fixed. So here, it is in time domain. So if we want to analyze, we cannot keep it in time domain, we must need to convert it in S domain by using Laplace transform. So the Laplace Ms is equal to, we can write it Kp into Et will be converted into Es, which will give you Ms by S equal to Kp. So Kp is constant. What is Ms and Es? This is called transfer function. Controller transfer function. Controller. The controller transfer function. We are dealing with this. I already told you that. We are dealing with this only in controller. Today's lecture is based on this. We are not talking about this whole control system. We are only talking about this control system. So what is this? This is the input. And empty, what is that? This is output. And how do you get output? For the proportional control, it is having a linear relation. Linear relation. It is proportional. Input and output are proportional. That means empty is proportional to Et. Where we can write it empty equal to Kp into Et. Kp, what is that? It is a proportional constant. So we can apply the Laplace transform and we get it Ms by S equal to Kp. Common, very simple. So this Ms by S, what is that? Output by input. This is output by input. And that is what we call a transfer function. What is a transfer function? The ratio of output and input, right? It is called a transfer function. Transfer function is the ratio of output and input in Laplace domain, in S domain, not in time domain. So that is basic proportional control. Now, what happens in the ground mostly? Look. Now, look at this. This is mostly we call it TD. TD is delay. Delay. Time delay. Delay time. But after the delay, once the gain increase, this is what? This is gain. This is gain. Or set point. Now, while suddenly the gain increase, what will happen? Steady state error will increase. Steady state error will increase. Now, if the gain is increased, what will happen? In the output will become like this. The output will become like this. Look, the output. Before it is like this. Before it is like this. The rising time is very high. What is this? This is called rising. Rising time. The rising time is very high, very large. That means it is slow. But while we use a proportional control, it responds faster. The system will respond faster. Now look at this. This is P control. P control. If we use a P controller, then look at this. The rise time becomes shorter. That means what? The system is responding fast. System respond fast. But there is a problem. While it respond fast, it oscillate. Look, it start to oscillate. Our system needs to be stable, fixed, stable. But here it is oscillating. That means what? It is unstable. It is unstable. So there is one advantage, one disadvantage. What is the advantage? While we use a P controller, the rise time will be shorter. System will respond fast. But the disadvantage is while it will respond fast, it will oscillate. It will not be fixed. Makes it an underdamped system. How do you call it an underdamped system? If zeta value is greater than 0, less than 1, that is, we call it underdamped system. So makes it an unstable system. Unstable. So this is the problem with P controller. It is a problem with P controller. But advantage is the system will be fast, very fast. Now, the problem is we already know the system will eventually unstable. So, what do we need? We need to use another controller with this proportional control. With proportional control, we need to use another controller like integral control. What is the integral control? Integral control are having an output rate of change. It depends on the magnitude of the input. That is, we already know that y is proportional x dt. This is what we know. So, look, the system input, this is E. And this one we can write it MT is proportional integration of ET dt. Integration of ET. What is E? Input. And what is the output? MT. So see, the input is like this, but in the output it is like this. Output is like this because we have a rate of change. So this one we need to apply the Laplace transform. First we see a smaller amplitude input causes a large deviation, a slower rate of change here, this here in this side. Suppose here T0 to T1. Look, T0 to T1, small changes, but T1 to T2, the change is high. And why it will increase like this? Look, then T3, it will be more high, so it will increase. Because it is changing in this way because of the integration. So if our input error, if the error is small, then the changes will be smaller. Changes in output will be smaller. Now, how can we explain it? Okay, I'll show you that later on. The major advantages of the PI control is it is having an unique ability to return the set point. Set point means what? In the game. So it will return to the game by following a disturbance. This is the advantage. That means here, this, it will reach to here. No matter wherever it is, the gain, it is here or there, or higher or lower in the output. Eventually it will reach this point. We need that because we need unity gain. Unity, output by input, unity, 1. Output by input, 1. So it has to reach to the point. So input and output reach to single point. Disadvantage is it is very slow. it is very slow because of the integration. So this, because of that, it will lead a system instability as well. So there is a disadvantage, because if the system does not respond fast, it will make much more error. Even though it is reaching to the same output, again, same point. But if it is slow, then what? It will make some error. So this integral control does not use alone, it will be combined with proportional control. That is why we do not use only I, we use PI together. So if we use PI together, how can we define it? Look, here we have an error, steady state error. This error here, it will send to two control parallel. It will be sent, this same error, it will be sent to two controller, and then here there will be an output which will combine this. What is this? Summing point. The summing point will combine this. So suppose this is I control. So I control will provide an output MI, and P control, this is P control. It will provide an output MP. So what is total M? MT. MT will be equal to MIT plus MPT. Total output, this. So what is MI? MI T is proportional ET dt. Integration of ET dt. So we need to use a constant term. MIT is equal to Ki integration of ET dt. Now it is in time domain. So what we need to convert it in as domain. So but I will show you that later on. So here this is 1, and we already have in last slide we have seen that proportional control output is KPED. So together MT is equal to here. This is MPT, and this is MIT. Here. Together we can write that. Now it is in time domain, so what we need to convert it in Laplace domain. So here, apply Laplace. Transform. So if you apply Laplace transform, what you will get here? M, it is M, greater one, M, S is equal to Kp into Es plus Ki into Es by S. So Ms will be equal to Es into Kp plus Ki by S. So you will get a transfer function Ms by Ds. know that the integration of ET dt is 1 by s. Integration, if you have integration, if you do the Laplace, then it will be 1 by s. Alright, the next one is the derivative control. The derivative control, PD. So in PD, again the same thing will happen. Here, this point will send both. But now here we have D control, D. So D control will give you MDT, and this is MPT. So here you have the MT, which is MDPT plus MPT. So what is MD? MD is the derivative control. MDT is proportional to D ET dt. Derivatives. This is the derivative. So d et dt. So here you will get it mdt will be equal to kd into d et by dt. So now add both kp et and kd into d et dt. Again apply the Laplace. Apply Laplace because we need to find out the transfer function. So if you apply the Laplace here, Laplace transform, it will get ms is equal to kp into es plus kd into what? If we apply Laplace to derivatives, there will be an s, right? S into es. Look, the Laplace of dy dx or dx dt. What do you give? What do you get? Laplace of dx dt. What do you get? Anyone? S into x, right? You will get an s. We already know in mathematical modeling we explained that. Laplace transform of any derivatives, you will get an s. Laplace transform of integration of x dt, you will get 1 by s into x's. So this is a common one. Remember it if you can memorize, if you cannot remember that, because these are the common one. You need it all the time to while you use the derivative, while you use the integral, the Laplace transform derivative and integral will be like that. So now here you can write it as equal to es into k p plus kd into s. So you will have a transfer function is ms by s into kp plus kds. Now what is the advantage of this PD control? Now look at this PD control. Here. This is what you will get by using PD control, the output, controller output. This, what is that? This is P control. This is P control. Now, why do you use a PD control it does, it is having one very important advantage. It will look, what is that? This is called overshoot. This overshoot in PD control, there is no overshoot. So it will reduce the overshoot. This is one very important advantage. It will reduce the overshoot. And if we use the derivative control with the proportional control, it will make the response like what? Like critically damped. This is critically damped. Critically damped. What is that? Zeta is equal to 1. Critically damped. Zeta value is equal to 1. So it will make it critically damped. It will reduce the overshoot. But there is a problem. Look. Here. Here. It does not reach to the set point. It does not reach to this point. This is the gain or set point. It is not reaching to the set point. That means there will be a steady state error. There will be an error. This is the error. PD control will make the system output. The controller output is critically damped, which we want, but it does not reach to the gain or set point. We must need to make sure that it reaches to this point. It has to reach to this point. Otherwise, there will be any steady state error. So it is lower. And this is the disadvantage. This is the disadvantage of the PD control. So because of this problem, because it does not reach to this point, what do? We combine I control. So that this I control will make it here. Because I control makes it the same as gain. It will reach to the same as gain. It is stable, but it is not reached to this point. So this point can be reached if we use I control with PD. That's why we need to use PID. That is the reason we need to use PID. So here, the higher the error signal rate, the sooner the final control element is positioned to the desired value. Here we have the higher error signal. This is the error signal because this is the input now. This input will make an output like this. Problem is, I already told you, the advantage is it will reduce the overshoot problem. It will reduce it and it will stabilize the output. Stabilize. Here, this one. It is stabilized now. It is fixed. But it is not reached to the set point. So this is the problem. This problem can be overcome if we use a PID controller. So PID control can be used to mitigate that problem. Why? Look, I already told you that in integral control here. Integral control. This is the integral control, right? No, here. In the integral control. So it does. So in the integral control, it reaches to this point all the time. It will reach to this point. So we will talk about the PID control after the break. Stay aside.